Hello everyone, this is a lecture course for Organic Chemistry Laboratory. This week's lecture focuses on synthesis of tetraphenylcylopentadieneone. So this part is also a continuation of the previous experiments that we have been doing throughout this semester, and to summarize about the processes, our target compound hexaphenylbenzene is synthesized from two major precursors, the diphenylacetylene and tetraphenylcyclopentadieneone, and we have finished synthesizing the first reagent already, and this experiment is one of the steps in the process of synthesizing the second reagent. And specifically, in previous week's experiment, we synthesized benzoin from benzaldehyde, and then benzyl from benzoin. And this week we'll look at synthesis of tetraphenylcyclopentadieneone from benzyl and 1,3 diphenyl propanol. So the general reaction is a condensation between two ketones, where benzyl itself is a ketone of two carbonyl carbons adjacent to each other, whereas the 1,3 diphenyl propanol is a pure ketone of a familiar type. And then the reaction begins by converting the ketone into a nucleophile. We do that by adding a base, where the base takes the proton and then creates a negative charge. This negative charge will make a nucleophilic attack into the carbonyl carbon opens, and this intermediate will be formed in the first step. In the second step, the opened oxygen negative charge takes a proton from the solvent that will be used in this reaction and becomes an aldol. This is actually a complex compound that have alcohol and aldehyde characteristics. That's why it's called aldol, right? So this aldol can remove water molecule from the overall structure, and that will be done by using a base. Again, abstract an adjacent hydrogen. The hydrogen leaves its pair of electrons, making a newly pi bond. As a result, the hydroxyl group leaves, and then we have a second fragment, kind of combination of an aldehyde and a ketone and that of an alkene. In this reaction you can see two curved arrows and one straight arrow. The straight arrow is for abstraction of hydrogen. When hydrogen is abstracted, a carbon anion will be formed, and then when this negative sign or negative charge delocalizes and that pushes the OH group to leave, this kind of reaction is actually called elimination, first order elimination through carbanion. Normally here the base and the substrate are involving, and it is kinetically it's second order, but because the mechanism proceeds through stepwise, that's why the E1 is put for that reason. And so the intermediate in step 3 will further react with the base. The base takes a proton and we have a negative charge, and this will lead us to the product, the cyclic product, with when this negative charge attacks the carbonyl carbon, a 5-membered cyclic will be formed, and again giving another intermediate close to the product. What happens is when this negative charge attacks the carbonyl carbon opens, and then this is two steps far from the final product. And that is when this negative charge abstracts a proton from a second mole of the solvent and becomes OH, and again a base comes, the base abstracts, this byproduct from the solvent, when the hydrogen is abstracted. Let's say this is ethanol, and when hydrogen is abstracted from ethanol, from the hydroxyl group of ethanol, it will be ethoxide, and the ethoxide will again react with a hydrogen in the substrate compound, and then make a negative charge, and the negative charge again delocalizes into the carbon sigma bond, making a pi bond. As a result, the OH group leaves, and then that will give us the final product. Still, two of the reactions we saw here in this slide and in the previous slide have the same mechanism, and that mechanism is abbreviated as E1CB, meaning elimination through carboanion. The conformation result for the product is a purple color solution, and that is an indication of this highly aromatic formation of this aromatic compound is stabilized by resonance. In fact, the first resonance for this compound is where the oxygen opens and pulls the pi bonds towards itself, and as a result it creates an electron deficiency within the carbon, which also makes the structure to be transformed to anti-aromatic, because if you count the electrons in the resonance contributor, they do not satisfy the 4n+2 rule, but they do satisfy the 4n pi rule, which means the compound now is anti-aromatic. And fortunately, this resonance contribution is helpful specifically in this reaction, because the second resonance contributor is what reacts with the 1,2 diphenyl acetylene to give us the final product for the long mechanism that we have been working throughout this time. So in the experiment, we'll be adding 1.05 gram of benzyl and 1.05 gram of dibenzyl ketone, followed by 20 ml of ethanol, our solvent, and the base, which is potassium hydroxide, about 0.15 gram. Actually, exactly, we have to add 0.15 gram, followed by 2 boiling chips, because the experiment is going to be conducted in a reflux setup, and for the instrument to be safe, we need boiling chips. The reflux experiment will run for 15 minutes, and after that we will expect a deep purple color solution. And this deep purple color solution can be cooled after 15 minutes, and then once it is room temperature, we can then further cool it in a nice bath, and we can then wash the solution to get crystals. It's good to use same amount of mixture of same amount of water and ethanol here to wash the product, and then once we have the crystals we can allow them to stay to air dry. Hopefully it will take some time, and either we have to let it stay overnight, or we have to wait for a couple of hours for it to dry. And we will be calculating the percentage yield for our experiment, and to do that we will need an actual yield from this experiment and a theoretical yield from the reaction, and that's why we need to weigh the product at the end of the experiment. We will not be doing any recrystallization, but we will be conducting melting point to see how pure our product is. But for the next experiment we can use the same product without the need to recrystallize it further. And yeah, the safety matters for the experiment is that we have used potassium hydroxide, which is one of the strong bases, and because most of the strong bases are corrosive to our tissues, we need to be careful in this case, particularly by wearing gloves. As usual, we'll do a spectroscopic study for our product using IR and NMR, and because our product is also a complex compound containing an aromatic structures, it's also good to do UV visible for the structure in a chloroform as a solvent. That's all for this lecture. If you have any questions, please you can email me, or you can put as a comment in the YouTube channel.